So again, hopefully you can find all of these slides on Sakai. I just made a couple of changes to some things just now. So the updated version will be on Sakai right after class. Right? But let's just start with just some announcements about a couple of things here. So of course, Wednesday's lesson is on YouTube now. Remember, I did not record Fridays because I really just wanted to let that be a time where we could just talk about some problems. But Wednesday's lesson is up on YouTube. I'll have office hours at the usual time, usual place, so right after class today. Excuse me, and then also 45 this afternoon. Mentor sessions are at the same time. As usual, Sunday, Mondays, Tuesdays, and Thursdays from 6 to 8 Pacific. And just a quick reminder about the homework assignments and the problem set. So there is another homework assignment due today by 5 p.m. And then the last one will be due this coming Friday. If for any reason you're behind, you need more time, I am totally flexible. So I would say don't stress out over any of this at all. I know I am really behind myself. So just take as much time as you need to kind of get all of this stuff done. And finally, the final problem set we're going to present in class on Wednesday, April 22nd. So in about another week and a half or so. But these should be all of the assignments due. So I wanted to spend a little bit of time going over the final presentations just to kind of remind you where we are there and what's happening. So remember that I would like for you to give presentations roughly at the end of the course. I would like for them to be video presentations, but feel free, you can either do them live over Zoom right now, or you can record the videos and then upload them into Sakai later. Whichever you feel more comfortable with, I am totally fine with. All that I ask is that, number one, you pick a group. This could be anywhere from 2 to 4 people, so whoever you would like. Number two, pick a topic, and I'll remind you the list of topics in just a minute. And then number three, be prepared to give a 20-minute video. So what I'm thinking is that it should be roughly something like 20 minutes with about 5 minutes questions and answers. That's if you do decide to do the video here during Zoom. And the topics I had listed in the course syllabus. So a lot of these here do look a little bit strange, but of course what I'd like for you to do is to learn about them and then present on them. So you should be able to learn about these pretty easily by going to Wikipedia. I think some of the stuff is also in the textbook. If you don't like any of these topics and want to do something different, I am perfectly happy with that. Just send me an email and I'm willing to work with you on figuring out what's what. All that I ask is that you get back to me with the topics sooner than later, because different groups might overlap in terms of what people would want to cover. And of course, we are going to do all of this roughly the last 2 weeks. So the plan right now is that we'll have problem set 6, which we'll do in class April 22nd. I'll then pass out the final midterm that Friday the 24th, give you the weekend to work on it, and then we'll start doing presentations as of that Monday, April 27th. So that being said, let me maybe just kind of ask for your general feedback on this, because this is what I've been thinking. I personally am just very behind, and I do apologize that I haven't had time to grade the midterm yet. I was wondering, instead of requiring both the second midterm and the final presentation, just giving you the option of doing one versus the other. And then this way, say if you really, really want to work with somebody in terms of doing the presentation, you can. If you feel that you're just way too behind, way too swamped with things, you don't have time to do a video, I am perfectly fine with just saying you can just do the midterm. The midterm will be just like with the first midterm. It'll be 3 problems, take home, open book, open notes. You'll have the weekend to work on it. But I'm just wondering your thoughts on all of this. Just saying doing either the midterm or the final presentation, but you don't have to do both. So any comments, any questions?
Yeah, personally, I think I really like to have the choice.
Okay.
Yeah, because it could be like a lot more difficult to organize and get together to work on things during this time.
Right. Okay. All right. And any other comments?
Yeah, I think I agree with that. Like it makes reduces the pressure on us,
Mm-hmm.
and the amount of things you have to do for the class.
Okay. All right, and that's what we'll do then. So I'll send out an official announcement about this. I mean, I will say, I do feel bad that this is supposed to be a speaking intensive class, and now things are kind of set up where it is going to be very difficult for us to do these presentations. But I do know that a lot of us are just really stressed in terms of trying to get things done, and I think that this will just make it easier on everyone. Um, so there's a question here about whether the final presentation can be used as a bonus since the topics will be harder. I'm happy to do that. So certainly if you do want to get the extra credit for this, I'm more than happy to do that. I'll be honest, I most likely am going to grade both the first and the second midterms very, very lightly. So chances are almost everybody's going to get like a 90% on both of those exams. So I don't really know if you'll need the extra credit. But if you do want to do the final presentation, that is, if you do want to do both the presentation and the final of the midterm for a bonus, I'll be happy with that. So I'll come up with more details and I'll put them online with Sakai in terms of like how the grading scheme is going to work and all the rest of that. But let's just say for the moment that you have the option for doing one or the other, but you don't have to do both for now. Any other questions, comments before we move on then? Okay, well, yeah, thanks very much for your feedback there. Okay, so let's try to do a recap of where we were. I want to slow things down a little bit today because actually we've covered all of the material that we need to cover for the last two homework assignments and for the problem set. So at this point from here on out, we really are just kind of covering different topics to see how all of this might be related to other areas. But really, as of last Friday, we've covered all of the new material that you'll need for the rest of the course. I definitely want to spend a little bit more time kind of slowing back down a little bit, maybe going over a couple of problems from the homeworks, from the problem sets. But really, there's no other new material that you'll really need to know from here on out. So let's let F here be a complete ordered field. So of course, this just means that we can think of F as like the real numbers. And we started to discuss last time about Cauchy sequences. So to begin with, remember that if we had a convergent sequence, then we know that given a positive number epsilon, there exists a delta so that xn minus xm is less than epsilon whenever m and n are greater than delta. So this is just a fancy way of saying that if you have a convergent sequence, the terms in a sequence get closer and closer and closer together. Right? That's all that's happening. The terms get closer and closer together. Conversely, we say that a sequence is a Cauchy sequence if exactly what I wrote above happens. So given epsilon, there exists a delta such that xm minus xn is less than epsilon whenever m and n are greater than delta. Right. So I'm just kind of repeating the words of what I had before. That's what it means for a sequence to be Cauchy. So again, the idea of Cauchy is the terms get closer and closer and closer together. Right. So the next statement is that Cauchy sequences are very nice. And if you have a Cauchy sequence, it is both a bounded sequence and it is a convergent sequence. So again, Cauchy sequences are really nice. They're bounded sequences and they are convergent sequences. So if you're confused for any reason at this point, just remember that the following are equivalent. It's a convergent sequence if and only if it's a Cauchy sequence. So they're one and the same. If you have a convergent sequence, then what that means is given epsilon, you can find a delta such that xn minus L is less than epsilon whenever n is greater than delta. The main thing to remember about a convergent sequence is you have to know at the front end what its limit is. You can't go any further when you're proving that a sequence is convergent unless you already know at the very beginning what the limit is. Cauchy sequences, on the other hand, you don't need to know what the limit is. All that you need to know is that the terms in a sequence get closer and closer together. So this is more like a philosophical thing of if somebody were to give you a sequence and you were to prove whether it's convergent or not. So if somebody gives you a sequence, one way to prove that it converges is that you know at the very beginning what the limit L is supposed to be, and then you just run through this whole epsilon delta definition here. On the other hand, let's say that you don't know what the limit is. Then all that you have to prove is that the terms in the sequence get closer and closer together in this epsilon delta sense of it. So it just depends upon what you feel more comfortable with. If you know what the limit is, you can do it one way. If you don't know what the limit is, you can do it a different way. Right. So there's a question here about, isn't this true for fields without the axiom of completeness, like a sequence that converges to root 2 but does not converge into rationals, but is still Cauchy? So this is a little bit subtle. Yes, it is true that you can talk about a Cauchy sequence but not have a complete field. So in this class, we really are only going to do Cauchy sequences if we have a complete field, right? That's why I kind of started this here at the very beginning. The reason being, you can have a Cauchy sequence that doesn't have a limit. And we want to make sure here that all of our sequences that converge do have a limit. So it is a subtle question, and it is true that yes, you can define a Cauchy sequence if you don't have this adjective here, complete. But for this course, we really are only going to define Cauchy sequences if we have a field that's complete. So that is a good question. Okay, any other questions here? Okay, all right, so again, this is the idea of Cauchy sequence versus convergent sequence. Now, we also stated that there is a way in which we can relate all of this back to defining real numbers. Remember, one way in which we define the real numbers was by using Dedekind cuts. So what I want to remind you is that I can also define the real numbers by using Cauchy sequences. And I want to run through a couple of arguments here and then work through an example. So we talked about this on Wednesday, but I just want to go through these slides all over again to kind of remind you how all of this goes. So first, let's observe that if we had a constant sequence, so every term in the sequence is the same, then this is a Cauchy sequence and therefore converges. So again, let's say that we have a sequence here, let's call it A, where every term in the sequence is this fixed rational number Q. Right, so it could be like the sequence that looks like 2, 2, 2, 2, just the number 2 that's repeating. So again, it's a Cauchy sequence because the difference is 0 for all natural numbers m and n. And so then if I stare at that, then I see that the limit here has to be this fixed number Q. So every constant sequence corresponds to the rational numbers. So I'm going to think of the rational numbers as the same as constant sequences. Right, so that's one observation. Next, more generally, let's say that S is any non-empty set collection of rational numbers that has an upper bound. So we can think of S as maybe a Dedekind cut. Right, doesn't matter, just let S be any non-empty set with an upper bound. So we know that over the real numbers, that L here has a least upper bound, sorry, S has a least upper bound, which we can call L. So let me define a sequence of rational numbers as follows. I want to choose here epsilon n to be 1 over t to the n. And since L is the least upper bound, I can find rational numbers xn, where xn plus epsilon n is greater than or equal to L. All right, so here I'm using part of the definition of what it means to be a least upper bound. So I know that each of my xn's here is less than or equal to L. So the statement is that I can always find an xn where If I add it to epsilon n, now it's greater than L. Right? That just means that my upper bound has to look like it's very close to the elements in the sequence. And so now this here gives me a Cauchy sequence whose limit is L. Right? So I'm going to come back and I want to talk about this here all over again when we do another example. Okay. So conversely, if I'm given a Cauchy sequence, I can actually define a Dedekind cut. Right, so this actually does say, if I start with the Dedekind cut, I know how to write down a Cauchy sequence. Now, conversely, what I'm going to say is if I start with the Cauchy sequence, I can write down a Dedekind cut. So we can do this as follows. Start with the sequence A, and let's consider the following set S. So S will be the set of elements where they are less than or equal to xn, where xn is just going to be something in the sequence. So this looks like everything just kind of to the left of all of the terms in the sequence. I should really say to the left of some term in the sequence. So then here S is a Dedekind cut because it's a non-empty set with an upper bound. And actually, the least upper bound is the supremum, but it's also the limit of our Cauchy sequence. So again, this says if you start with the Cauchy sequence, you can write down the Dedekind cut. Right? So they're all one and the same. Right? Everything here is one and the same. So what I want to emphasize finally is that we're going to identify the real numbers with one of two things. Either the collection of Dedekind cuts or the collection of Cauchy sequences. Right, so remember how if we had Dedekind cuts, we had this weird thing of we can add them together, we can multiply them, but that was a nasty construction because it was really hard for us to define addition and multiplication. On the other hand, I'm going to remind you in just a moment that with Cauchy sequences, we can also talk about adding Cauchy sequences, multiplying Cauchy sequences. And so that's why we can talk about kind of an arithmetic there. It's a little bit easier for us to work with. If you're wondering very specifically, how do you actually compute a real number? So here, this is not like this weird abstract definition of like Dedekind cuts or Cauchy sequences. Let's say at the end of the day, somebody asks you actually compute this thing. Here's how you do it. If you have a Dedekind cut, you look at its supremum, or if you have a Cauchy sequence, you look at its limit. That's how you would compute a real number. So if someone asks you kind of what the definition of a real number is, you could define it using Dedekind cuts, but if you wanted to compute it, you would compute its supremum. If someone wanted to ask you how do you define using Cauchy sequences, you could do it that way. And if you want to compute it, you just look at the limit. Right? So those are the two ways in which you can define real numbers if you want. Okay, right. Any questions on this discussion here? Okay, let's try to work through maybe an example here. And this is actually one of the problems for the homework assignment that's due today. Now, this is one way to do this problem. This is not the only way to do it. There's many different ways to do this problem. But I want to go over how you might do problem number 1. So here, let's fix an element D that's positive. And we know that the square root of D is the supremum of this set. Right? The set of rational numbers that are positive such that Q squared is less than D. Right? So worked out a couple of ways that this here was the supremum. I want to prove that there is a sequence of rational numbers whose limit is the square root of D. Right? So again, there's many different ways to do this. So I'm just going to give one method of how to do this. Right? Well, let me just first step back and let's just make a general observation here. Given a non-empty subset S that has an upper bound, then we know from our completeness axioms that it has a least upper bound. So let's call that L. Right? In particular, we have two properties about this upper bound L. Number one, every element in this subset S is less than or equal to L. And number two, given a positive number epsilon, I can find an X epsilon such that X epsilon plus epsilon is greater than or equal to L. Right, so remember that there was a previous problem set where we worked out these two properties. This is what it means to be the least upper bound. Right, that we have these two statements here. Okay, so again, this is just a general remark just to kind of remind you this is what we mean in general for any non-empty subset that has an upper bound. Okay, so in particular, let's let S be this set here. Right, so the set of rational numbers that are positive and their square is less than D. So we know from previous homework sets and problem sets that its least upper bound is the square root of D. Right. So let's do this trick here. For n being either 0, 1, 2, 3, so on and so forth, let's denote epsilon sub n as the following. Right, so again, for n being 0, 1, 2, so on and so forth, let's let epsilon n be this. Then according to what I just said earlier, I can find rational numbers q in S, where qn plus epsilon n is greater than or equal to L. Right, again, this is just the definition of what it means to be least upper bound. So I can find my qn's that would be a little bit, well, as close to L.
What is the reason that you selected that epsilon, 1 over 2 to the n?
Only because I just want something that goes to 0.
Okay.
I could have chosen 1 over 3 to the n. I could have chosen lots and lots of different things. But yeah, you'll see in just a minute, it actually doesn't matter. Okay. So now we've constructed a sequence of rational numbers where qn minus L is less than this here epsilon n. So sorry, this here was the typo. This really should have been epsilon sub n. Right. But again, here now I've constructed a collection of rational numbers such that the absolute value qn minus L is less than or equal to epsilon n. Okay. Now I'm going to use a couple of other problems that we've worked on. The epsilons here are a sequence of positive numbers, and actually you just showed problem set number 5 that the epsilon ends here tend to 0. Right, it's actually problem number 3C, problem set number 5. So we know that the epsilon ends here tend to 0. But the next problem on our homework set number 11, problem number 2, says that if you have this here, where epsilon ends tend to 0, then qn here tends to L. Right, that was problem number 2 on this week's set. Okay, any questions on how I work this one out here?
If we have a sequence of epsilon sub n's that tends to 0, then we know that for any epsilon that is larger than 0, we can find some epsilon sub n that is smaller than epsilon. So why do we have to go through the step of choosing a sequence that converges to 0? Like,
so think of this in this way. What you just stated is problem number 2. right? The whole thing that because epsilon n goes to 0, then I can choose an n large enough that epsilon n is less than epsilon. So that is problem number 2. What I'm saying here is, let's say that I don't want to go through the whole thing of proving that, like, for any epsilon that I can find an n where so on and so forth is going to be small. Let's just say that for the moment that I know that my qn minus L is less than some number. Not epsilon, but less than some number involving n. This is kind of like what we did with problem number 1 on problem set number 5 with the squeeze theorem. That the whole point here is that maybe I don't want to prove something in terms of epsilon delta. I just want to prove that what I have here is less than something that I know gets really, really small. So this just says that this allows me to do a little bit easier work. I don't have to do the whole thing of saying, let epsilon be given and then try to prove something. Right now, all that I'm simply saying is, I've just written down the sequence here. I have the statement here in terms of this inequality, and that's all that I need. All right, so it just makes my life a little bit easier.
And another question is, can we construct this sequence A to make it monotone increasing?
You should be able to. So we also did this in class, and I'm going to try to talk about this a little bit later on today as well. So yeah, you can definitely do it so that Qn is monotone increasing. You don't have to, but you certainly could. Right. What I'll actually say is you can basically choose a certain subsequence that will be monotone increasing. That's just going to be the Bolzano-Weierstrass theorem. So once you have the sequence A here, you know that this converges. So that means that it has a monotone increasing subsequence. So you don't have to worry about constructing it. You can always say one exists. Okay, but later I'll explain how to construct it. Okay. Any questions then? Okay, right, let's try to keep moving on here. So remember that with the Cauchy sequences that we have, we can actually use this to form a nice complete ordered field. Right, so again, if we let our script F be the collection of Cauchy sequences, then we know that we do have a complete ordered field. And just to remind you, there's a lot of work involved in proving that something is a complete ordered field. You have to worry about these 14 axioms. And instead of trying to do all of that, I just want to remind you that really there's 2 that we care about. There's closure under addition, and then there's closure under multiplication. So I just want to quickly remind you how those 2 go. So if we have 2 Cauchy sequences, call them X and Y, I want to prove that the sum here is also a Cauchy sequence. All right, so yes, we did do this Wednesday last week, but I just want to remind you how the proof goes here, because we're going to be using this trick over and over again. So remember that if you want to prove that something is Cauchy, we have to kind of go through these 3 steps. So first, we always start with just the standard statement, let epsilon positive be given. Right? You don't really think about it much, just kind of write that down to start with. Next, we need to choose our delta in a clever way. Right, so we're going to choose our delta as the max in this way here. So because we have a Cauchy sequence, then we know that we can choose a delta 1 so that xm minus xn is less than epsilon over 2. And similarly, we can choose a delta 2 so that xm minus xn is less than epsilon over 2. So let's just pick the delta to be the larger of the 2. Right, so again, that's the next step, is that I need to explain what is delta. The third step is that I actually have to prove that it works. So you typically start by saying, for any m and n greater than delta, you then have to go through some argument. Right, so in this case, then I know that xm plus ym minus xn plus yn, I have this here in terms of the triangle inequality, right? So I can just kind of break things up here. And each one of those separately is less than epsilon over 2. So the sum here has to be less than epsilon. So what I've proven now is that this quantity here is less than epsilon whenever m and n are greater than delta. Right, so remember that that's how a proof goes, that I really need these 3 steps. First, start with epsilon positive being given. Second, I need to choose my delta in a clever way. And third, I need to make sure everything works the way it's supposed to. Okay, all right, so any questions on how we did this here in the sum of Cauchy sequences? Okay, all right, let's move on here. So what about the product of 2 Cauchy sequences? So we're proved now that the product here, where of course the nth term just looks like take the product of the terms, that's also a Cauchy sequence. So same idea, we need to do this in 3 parts. First, let's assume the epsilon here is positive. Second, now it's going to be a little bit subtle. Cauchy sequences are bounded, so there is some number m sub 1. And I'm going to use that to then say I can choose a delta 2 so that ym minus xn is less than epsilon over 2m1. Right, so I'm going to be a little bit careful to kind of combine things in this way here. So if I write my delta as the max of these 2, then whenever m and n are greater than delta, we're going to write this very clever trick here. So xmym minus xnyn, I can write in this way. So xm minus xn times ym plus xn times ym minus yn. All right, so just kind of a trick just to get everything to work out nicely. So now we'll just use the triangle inequality to write this here. And then now we just write in all of our substitutions, right, in terms of m1 and m2. Right. So now we're able to conclude that this difference here is less than epsilon whenever m and n are greater than delta. Okay, so any questions on how we work this out here? I just wanted to kind of remind you, these are how the proofs would go if you want to prove like the product of Cauchy sequences is Cauchy or the sum of 2 Cauchy sequences is Cauchy. All right, so please keep in mind that you'll probably need these for problem set 6. Because problem set 6 does say a little bit more about these Cauchy sequences. All right. So what I'd like to do today is try to combine some of these ideas together and hopefully relate back to some things that you've seen in your calculus classes. This is this whole concept of continuity. So I want to start off with maybe some kind of intuitive ideas, and then we'll try best to jump into some serious definitions and then eventually try to work through some properties. So I'm going to show you a few different graphs here, and maybe if you can just kind of tell me verbally, or you can even type it in the chat window if you want, which of the following graphs is a continuous function? And I'm not going to worry about kind of the rigorous definition just yet. I want you to kind of just look at the graphs and tell me intuitively, do these make sense? So would you say yes or no, this is a continuous function?
Yes.
Right? Okay, yeah, yes. So yes, this is definitely a continuous function. All right, what about this next one here? So is this a continuous function?
No.
Right, yeah, no, it is not. So you can kind of see intuitively, there's like a break here in the middle, right? So it's like a part here where it's connected, a part here. There's kind of this thing here in the middle where things get screwed up. So no, this is not a continuous function. This is a discontinuous function. Right, so what about this next one here? So is this continuous or discontinuous?
Yes.
Right, yes, this is definitely a continuous function. Okay, and then what about this last one here? Is this a continuous function? Right?
No.
Okay, so why is this not a continuous function, would you say?
Like, I'm just remembering like the thing that we learned like way back in like algebra where like it couldn't go through a vertical line at 2 different points.
That's exactly right. Yep. So in this case, it fails the so-called vertical line test. right? So this actually is not even a function. So it's definitely not a continuous function because it's not a function, right? It has to satisfy the vertical line test. Okay, does that kind of make sense for these examples here? All right, so let's maybe try to go over some rigorous definitions, and I want to play around with some examples to get an idea of what's happening. So given two numbers a and b, we'll define the closed interval as this here. So it's just the set of numbers x between a and b, where x might equal a and x might equal b. Right? Now, sorry, jumped all the way to the end on me. Let's just go back through. Right? Given a closed interval, we say that our f here, going from a closed interval to our field f, is a function if f of x is defined and it's unique for every I in x. So this just means it needs to satisfy the vertical line test, right? So I don't want to say that if you give me an x, then there has to be a top and a bottom, that there have to be two, right? There should be exactly one element f of x, right? Now here's going to be the weird definition, and this is what I want us to play around with today. Given a point P in the closed interval, we'll say that our function is continuous at P if two things happen. Number one, it's defined at P, so f of P exists, right? It is defined at P. And number two, given a positive number epsilon, I can find a positive delta so that f of x minus L is less than epsilon whenever x minus P is less than delta. Right, so again, this will be kind of a weird definition, but I want to try to explain what all of this means. Right, so again, what this says is, if x and P are very close, then f of x and f of P are very close. Right, so that's the intuition here. Continuous at P means if x and P are very close, then f of x and f of P are very close. And finally, two more, we'll say that it's discontinuous at P if it's not continuous, right? If either one of these two fails. And we'll just say that a function is continuous on the closed interval I if it's continuous at P for every point P in the interval. Right, so that's what I mean by saying that a function is continuous. It has to be continuous at every point. Okay. So again, these are kind of fancy definitions, but I want to try to explain a little bit more by kind of doing some graphs and kind of showing you some pictures like what should happen here. Right? So any questions so far? Okay. All right. Let's see. Sorry, let me turn this off. It shouldn't be making any noise. So first, here's an example of a continuous function where kind of the idea is, let's start with maybe a point here, call it P. Right? So what I want to know is if I'm very close to P, so this might be my interval I, then I should be very close over here for this interval, right? So here what I'm doing is, let's just kind of create a box. So again, this here is my point P, and now I want to ask what's happening with the y coordinates. So my interval here, and then I have my y coordinates here. So now this says that maybe if I make a smaller box here for my interval I, then I have to have a smaller box here, right? So that's the whole idea of continuity, that if I get very, very close to this point here, then I have to get very tight inside of this region here. That's all that's happening in terms of what it means to be continuous. The epsilon delta thing is supposed to be fancy, but it's not any more complicated than that. Right, so let's try maybe a second example here. So here's going to be the same concept. Maybe if this is my point P, This might be my point P here. Then of course, I want my interval I to maybe be this. And then now we have to kind of ask what's happening in terms of the function. So if I'm very close here, then I should be very close here. Right, so that's, of course, what it means to be continuous. Now, the time where it gets weird, you can see is something like this. So maybe if I'm sitting here at this point, then this here would say is continuous, because see, if I get closer and closer, then of course this box here is going to get smaller and smaller. But now what if I'm sitting something like here? Then now you can see, if I have a box, I'll have some parts over here, and I'll have some other parts over here. And there's no way, even if I make my box tighter and tighter, then you see that I have kind of different stuff here, and then I have kind of different stuff over here. So the problem is that if my box gets tighter and tighter here, then I don't get closer and closer. I actually get further and further away. So that's why this one here will be discontinuous at 1, although it will be continuous at other points. Right, so again, just think of this as I have my boxes. If I get closer and closer, can I see what's happening? If I get closer and closer to 1 here, I get further and further away, so I can't really see what's happening. Right? Now, the way this is related to what we've been doing so far with sequences and series is as follows. Say that we have a continuous function f. Then this says, if I have a convergence sequence A, then the function also converges to that number. Right, so if my xn's get closer and closer to p, then my f of xn's get closer and closer to f of p. Okay, and I'm not going to worry about the proof of this for the sake of time. It's actually not hard at all. What I really want to do is show you some numbers so you can kind of see how this here works. So let's take a look at this polynomial here. F of x is x squared. Right, so this here we know is a continuous function because we've kind of looked at a couple of graphs of this. Let me take a look at the following sequence. So here, if you will, pick D here to be maybe a number greater than 1, and let's write down the sequence here. So remember that this is a monotone increasing sequence whose limit is the square root of D. Well, according to this theorem, the fn's here have to go to D itself, right? Just have to go to its square. So you can actually see this in terms of numbers. So let's say here's the case where D is equal to 2, right? So here's my n's. You can see here how xn's, they monotone increase, right? They're all going to 1.41421. And notice how the f of xn's also monotone increase. Right, so that's what that previous theorem says. That if I have a sequence that gets close, then f of the sequence also should get close. Right. Let's actually do this here, excuse me, with a slightly different sequence, so same function. But now let's consider this sequence defined in this way. And if you remember, this was a monotone decreasing sequence whose limit was also the square root of D. So we can try to do the same thing here, right? Look at numerically. So here you'll see that my xn's are monotone decreasing, and my functions here are also monotone decreasing. Right. So here's another part of that theorem. It's actually the corollary, a direct consequence, that says, say that we have a continuous function. Now pick a subset of our closed interval. So this might be a sequence or it might be something else. Pick any subset that you want. Well, if my function f is increasing, then f of the supremum is the supremum of the f's. Similarly, if it's decreasing, then f of the supremum is the infimum of the f's. So I just want to take kind of a quick minute and explain what's really happening here. Really what I've shown here is exactly the numbers that I showed on the previous slide. That if I have an increasing sequence, then f of the limit is just going to be the limit of the sequence, and so on and so forth. So here's how the proof here goes. It's actually not bad at all. I have a sequence. It's contained in a closed interval. Therefore, so I have a set S. Is contained in a closed interval, therefore S is bounded. If F is bounded, then S has a least upper bound. That's what we're going to call P. Once we have this P, we can find a convergent sequence whose limit is P. All right, this is how we started today's lecture. So again, once we have a sequence, a set S, we can find a sequence whose limit is P. So let me consider the following sequence. So here, I'm just going to take everything in that sequence A, and let's apply f to that. All right, so f of x0, f of x1, just apply f to everything in the sequence. Well, f is an increasing function, so this is a monotone increasing sequence. And actually, it's bounded above by this here, f of p. So we just got finished showing on the previous slide that the supremum here is the limit, right, which really is just this here, f of p. But p here, remember, is just the supremum of s. So this is a matter of we're just kind of combining like the Bolzano-Weierstrass theorems. Sorry, that's the first one here. And then the previous slide was the second equality here. Right, it's just kind of combining everything together. So here I just wanted to end up by saying that now we have these nice statements that allow us to say that we know how limits work in terms of sequences, in terms of these continuous functions. So if I have a nice continuous function, that's the same thing as looking at what's happening with these sequences. So we'll play around with this more on Wednesday, but I wanted to kind of introduce some of these ideas today. All right, so any questions on some of what we said today? Okay. All right, so if no questions, let's call it a day then. So on Wednesday, I want to say a little bit more here about continuous functions, and I want to go over some of the properties that they have. All right, well, you all take care and try to have a good rest of the day.
Thank you.
Okay.
Thank you.
Thank you.
Thank you.
You're welcome.
Hey, Professor Goins.
Oh, yeah.
So just to clarify, is the midterm, are the midterm and the presentation optional? Are both optional, or you do the midterm and the presentation is optional?
I would like for everyone to at least attempt one. You know, I mean, if people have real bad hardships and they can't do either one, I'm fine with waiving it. But I'm going to say I would at least like for people to attempt at least one of the two.
So at least one of them.
Yeah, at least one.
Both. Okay.
Yeah, that's right.
Okay. Thank you very much. Have a good day.
You're welcome. Right, thanks. You too.
Thank you.